Many people will take that as a transition from maturing to senescing. Because we know at the stand level, at least from forest management, that age of maximum mean annual increment is the point at which we maximize a perpetuity of yields. It's the same it holds for individual trees. So we can play with these ideas in all sorts of packages, but in Wolfram Alpha. So here's a graph of a particular function that will give us that sigmoidal shape. Not linear, right? You can't just use a straight linear equation. That's not going to work. So here we're saying size is this particular function of age or of time. So if we want to find this inflection point, which is kind of not shown too well on here, here's our size versus time. We want to find the point where growth is increasing at from an increasing rate to a decreasing rate. We take the derivative of that function and we get this result. And when we look at the two plots, here is size versus time. Here is change in size, growth versus time. So we have increasing at an increasing rate, and then still increasing, right? But increasing at a decreasing rate. So this point right here would be the inflection point on that curve.
What's the difference between EXP and E?
Same thing.
Okay.
Yeah. When we write E,
Yeah, I thought they were the same thing, but
we would write E to the X. That's the same thing as EXP. It's easier to write this because we don't have to worry about writing power. Okay. So this is what we would call cumulative size. Right? We're accumulating growth, accumulating size. And this is one particular definition of growth found by taking the derivative. So derivatives, remember, are instantaneous rates of change. Oh, right, we're going back to those derivative calculus lectures. Right? Instantaneous rate of change. So this is instantaneous growth rate. Instantaneous growth rate. If we actually want to find that point, we can take the derivative of that growth curve. We get this, which would be acceleration. Right? And we find out that the root of that equation is at age equal 10. So this point right here, we drop it down, is at age 10. Inflection point right there. Point at which instantaneous growth goes from increasing at an increasing rate to increasing at a decreasing rate. Okay, well, what's the problem with the calculus? The problem is we can't observe instantaneous growth, right? We're looking at intervals of time that go to 0. That's not something we observe, right? We go out and observe size of trees maybe every 5 years, every 10 years. So whereas that instantaneous growth rate is convenient from a mathematics point of view, we need to have other definitions of growth or of increment that relate to what we actually observe. So we have these three. CAI, current annual increment, PAI, periodic annual increment, and MAI, mean annual increment. So current annual, periodic annual, and mean annual. So this instantaneous growth rate, in forestry we call that current annual increment. Current annual increment. So when you see current annual increment, think of derivatives. We don't observe that. Well, you might say, well, I'll just go out every year. I could count. I could take increment cores, right? In some sense, that's approximating what that instantaneous growth rate is. But it's typically not something that we observe. PAI is something we can think about and get our head around. Periodic annual increment is change in size W is size. So it might be height of a tree, it might be DBH of a tree, it might be volume of a tree, biomass of a tree, whatever. So W is size, and we're looking at size at two different times, time 2 and time 1. So we take the change in size and then divide by the interval length over which we observe that size change. So of course there's not one periodic annual increment. There are periodic annual increments corresponding to different lengths of time interval. Question?
Oh, is the triangle the symbol for change or difference?
Yeah.
Okay.
Yeah. Right. Change in X. Mean annual increment, on the other hand, is just size at some time divided by that time. So, volume of the tree at age 20 divided by 20. Mean annual increment. These three different expressions of increment are interrelated. Periodic annual increment will go to, that's what I mean by this, will approach current annual increment as what?
Time decreases?
Pardon me?
Time decreases?
Yeah. The width of the time interval goes to 0. That's the definition of an interval, right? We let that change in X time here go to 0. So the shorter interval width we use, the closer that PAI curve will be to the CAI curve. Periodic annual increment will peak before mean annual increment. And then, of course, from that is also the fact that current annual increment will peak before mean annual increment. What do I mean by before? I mean time before, earlier in the life of the individual. PAI and also CAI go to 0. Mean annual increment does not go to 0, right? Because mean annual increment is just size divided by time. Well, I guess it does go to 0 as time goes to infinity, but for any reasonable time periods, it does not go to 0.